Hello, this video will be a short video on common designs that we can use to fit second order models. And again, you can find more details about these second order designs in your course book. First out is the central composite design, the CCD design, which has been mentioned in previous videos as well. The central composite design in two factors is illustrated in this slide. So we have factorial points. We have axial points, these red points, or star points, we sometimes call them that as well. And we have center points in this design. In general, we will have 2 to the k number of factorial runs. So in this case, with no replicates also in the factorial runs, we will have 2 to the 2 or 4 factorial runs when we have two factors. We will also have 2 times k axial point runs. So we'll also in this case have 4 axial point runs in this design for two factors, and typically we also have 3 to 5 center point runs in this design. The central composite design, or CCD, is perhaps the most popular design among the two second order designs because it can be assembled or built sequentially from a fractional or full two-level factorial design. So that's a very nice feature of the CCD design. We have another parameter that is important in this design, and that's the distance from the center here, from the center to the axial points. We call this distance alpha in this case. It has to do, for example, with if the design will block orthogonally, or if it is rotatable, and so on. Rotatability is a nice property of a response surface design. Because in advance we cannot know where in the design space the optimum will be located. So therefore rotatability makes sense. A rotatable design means that the variance of the predicted response values will be same given an equal distance from the design center. Or in other words, when we rotate around the design center at an equal distance, the variance of the predicted response does not change. Hence we have the name rotatable design. So that's an interesting and good feature. So if we can pick the alpha value of the CCD design so that we achieve rotatability. But that's not always possible to pick alpha freely. For example, it is sometimes difficult to go beyond the low or -1 and high +1 levels of the design factors for some or for all factors in a design. In those cases, the face-centered central composite design or face-centered CCD may be a good option. In the face-centered CCD, the alpha value is equal to 1. So this means that the axial points will be located on the cube wall exactly at -1 or 1 level. Here it's on the cube wall because we have 3 factors, so we can construct a cube. And we also have center points as an ordinary CCD, but the face-centered CCD has alpha value equal to 1. And that's very useful in some cases then when we cannot go beyond the -1 and +1 levels. We also have the Box-Behnken design, which is a design with 3 levels for each factor to build a second order response surface. So if we take a look at the design points required for that design, we can almost, in this case with the cube, we can almost see that we're trying to inflate a sphere inside of this cube. And when the sphere touches these axes of the cube, we have our design points. So the Box-Behnken design is considered to be good from an economical perspective. So we don't need so many design runs. And another good thing with the design is that there are no design runs in the extremes, like in these corners of this cube, for example, at the -1 and +1 levels of the factors. And that's sometimes useful. In some cases, that's very useful. So the Box-Behnken design is good in that way. The drawback with this design is that it typically makes sense to use it only if we start with a second order design directly. So this cannot be built sequentially, for example, from a two-level factorial design. So it's not perhaps as flexible as the CCD design. Okay, and many times blocking comes into play in response surface methodology and in the second order designs. For example, if we want to assemble or build a CCD sequentially, we may run, let's say the factorial portion of the CCD is run this week, and then we with some center points, and we see that we need the axial runs and some additional center points, for example, we will run this next week. And some time has passed, and we want to block this design to not have this potential process drift or whatever happens between those 2 weeks to affect the effect estimates. So we want orthogonal blocking in RSM. So the resulting, if we're able to block orthogonally, the resulting response surface design will be constructed in a way so that the potential block effect will not impact the effect estimates. And that's sometimes possible to construct, but sometimes we also need to choose between, let's say, a design that is either rotatable or a design that blocks orthogonally. Just a small example of this, how we make sure that the central composite design blocks orthogonally, and that's made through the alpha choice of alpha value. In this example, we are assuming that we have two blocks. In the first block, we have NF runs in the factorial points, and we have NCF center point runs. And in the second block, we have NA runs in the axial or star points and NCA center point runs. And this expression, if we pick the alpha value based on this expression where we have NF, NA, NCA, NF, NCF, and so on, and we calculate what alpha is, we pick that alpha value, then we make sure that the central composite design blocks orthogonally. So as you can see, the alpha value in the CCD design is an important design parameter for the CCD. All right, so I'll stop there, and I thank you for listening, and best of luck with the second order designs. Bye bye.